So welcome to the ZP and PalmSens webinar. We think this is the third in the series, and I say we think because I'm doing it from memory. So far, if my memory serves me right, we've done analysis of red wine. Actually, no, we've done caffeine. We've done caffeine so far. We've done glucose so far. And we like these webinars to be sort of, let's say, very interactive. We want to hear what people are interested in. So maybe in the comments or in the questions, say what you're interested in. But today we're going to do salinity, which is kind of nice because when you think about the caffeine work that we've done, for example, then we used a lot of cyclovoltammetry. So we discussed the Sensit Smart and its ability with the ZP screen printed electrode to do cyclovoltammetry. When we did the glucose work, we demonstrated the PalmSens Sensit Smart with a ZP glucose sensor, and we showed using amperometry that we could distinguish between Coke and Diet Coke. So if you're ever wondering in the future and you're at a bar and you're not sure if it's Coke or Diet Coke, then as long as you've got a smartphone, a Sensit Smart and a glucose sensor from Zimmer and Peacock, then you can answer that question. And today we're going to do salinity, so the sort of measurement of salt. And I think that's super interesting. I mean, the most measured chemical parameter in the world is probably pH. But saltiness is probably somewhere there as well, because obviously, you're interested in desalination for water. You're also interested in sometimes just answering what's the salt, just in blood, for example, but you're also kind of interested in the salt in food. So as I say, this is interactive. We had some feedback to the guys at PalmSens. They said people are very interested in salinity. And so today we're going to talk about salinity. We're going to talk about impedance spectroscopy, and we're going to talk about conductivity. And I think now that I will do a sort of a gentle handover, and I think it'll be to Lutz, but I also know that there's a few quizzes will be made available. So answer the quizzes when the guys kick in, but I think it's over to Lutz. So yeah, thanks very much. So I hope you look forward to this live demo, by the way. We will be measuring using the Sensit Smart these three solutions, and I think we'll come back to us shortly. Thanks very much.
Thank you, Martin, for the nice introduction. Yeah, I'm Lutz Stratmann, and I'm with PalmSens, and that was just Martin Peacock, surprisingly from the company Zimmer and Peacock, was talking to you. So we would like to start immediately with a little poll, just to see who's there today with us, if you're returning or if you're here for the first time. So it would just be great if we start the poll for that. So I'm going to move forward here, and today want to talk, as I said, about salinity measurements. We first want to start with what is salinity and give you a short theoretical introduction. Then we are going to move forward to the live demonstration that will be done by Solron, who's also, well, who's together with Martin physically again, because, well, fortunately a few rules are less during this time of the pandemic. Okay, so let's first have a look what is salinity. As Martin mentioned, it's a measure for the saltiness of a solution, which just describes how much salt is dissolved in the water. The units are usually grams per liter or grams per kilogram. The latter is usually dimensionless because, of course, if you divide a weight by a weight, you get like a ratio, so maybe promille or percent. I think many of you know, but some of you might not be chemists or just not very interested in chemistry before attending that seminar. So salts dissolve as ions. That means before you have in your solid a combination of charged and non-charged molecules or atoms, and when you put them in the water, they're going to dissolve into the two different charged parts. And that makes the water conductive. So I guess some people of you might know this, that very pure water has very low conductivity, can even be used as an insulating material, while ions make the water conductive. Then based on these conductivity measurements, so people said, okay, salt makes water conductive, so with conductivity we should be able to measure the salinity. And so the practical salinity scale, 1978, was introduced, which is based basically on empirical measurements, and uses as unit the PSU, which is not always accepted in the scientific community, so be careful when you use it, but you read it in a lot of places, so now you know what it is. The most common salt that we encounter is sodium chloride, and you have it maybe on your table when you have dinner, or you swum around it in the ocean. Okay, why would we be actually interested in salinity? Yes, you know, the ocean is salty and you need some salt for your food, but why are we interested in salinity from an industrial point of view, for example? Well, as we already told you, is it gives you, for example, the conductivity. It influences the conductivity of your solution. It influences the boiling point, and it influences the density of your salt solution. It can also indicate purity in the sense that what I just said is like very pure water has actually a very low conductance because there's no salt in it that makes it conducting. So, for example, if you want to have pure water, usually you have demineralized water. That means you removed all the salt from it. For corrosion, it's important because water with high salt content corrodes other things a lot faster. Then it's important for the environment, right? It's a different biotope if you have salty water, non-salty water, or a mixture of that. Then fresh water, I mean drinking water, is only available until a certain amount of salt is in there. And of course, salinity is an indication for health sometimes. If you have dehydration, also your conductivity values in your, body fluids will change. You can see that on the bottom right. You can see the indication, this is the conductivity on a logarithmic scale, and you see here indicated the range of certain types of water. With the thick line is the line between drinking water and non-drinkable water. And you see that, for example, a lot of like industrial used water, like wastewater, is not in that range of drinkable water, right? Concentrated acid as a comparison, and I mean, most of you know that you shouldn't drink that. Yes, and we have processed water and seawater, and yeah, just to give you an idea how the conductivity influences what we use water for. Okay, so how do we perform an electrochemical detection? Because all that sounds now very complicated already, and you're like, okay, how do I do an electrochemical measurement? Well, if you've been with the previous installments, most likely you have been, you now know that slide, but just for the ones that are new, you have a solution and you want to measure something in the solution. You need some electrodes, so the interface between the solid conducting parts and the and the electronics and the solution. That is so you have the solution, you have solid conducting parts, and behind that you need electronics to control it. So to apply a certain potential, to apply a certain current, and you need a software to control this. So on the left side you see like a general block diagram. On the right side you see what we're going to use today. We're going to use the Sensit Smart from PalmSens together with the software. PS Touch, that is an app for Android, and you see by Zimmer and Peacock, who have a good grip of the chemical part of the whole experiment and who are making and designing and developing electrodes. Okay, so the Sensit Smart, just to give you a short introduction before we move on to the more chemistry part, is based on the Pico, which is an OEM potentiostat module. That means you can use that module to build it into your systems and have then your own potentiostat in your own system without developing your own potentiostat. So you build, for example, a lab on a table or something like that. Based on this very small potentiostat module, we made the Sensit Smart, which is now like a USB stick size potentiostat, and it can actually perform the most common electrochemical techniques like cyclic voltammetry, as we've shown previously in the, that was for the, for which measurement was that? If you saw the red wine measurement, that is possible. Oh, sorry guys, we have, it seems there an emergency. Okay, it's gone. Okay, where was I? Yeah, so cyclic voltammetry we've seen chronoamperometry, and today we're going to look at electrochemical impedance spectroscopy. All right, Okay, let's have a closer look at electrochemical impedance spectroscopy, because it is a very popular technique, but also a very complex one, so some people might struggle with it. What we do is we apply a potential wave, in a sine wave, and then we measure the current reply. And usually you try to have a system, or you need a system where the response is linear, so you always also get a sine wave back. From these two waves, you can calculate the impedance, Z, and you can calculate the phase shift, phi, which is then read from the time shift of the two curves. Both values are actually calculated in the software, so you don't have to do it manually. You don't get the two waves. No, you get immediately the impedance and the phase shift. Usually what we do in electrochemistry is, because some people might know this technique from electronics, but in electrochemistry we need to superimpose these AC potential, this sine wave, on top of a DC potential that we are applying. Okay, usually you try to find an area where you get a very sensitive signal. This is indicated on the bottom left, where you have like the black curve is basically the Nernst equation, and then the blue waves are the potential, and you see that if we apply a very small potential amplitude at a very sensitive part of the IV curve, we get a very good current response, and this makes this a very sensitive technique. What you usually do is, and this is why it's called spectroscopy, is you scan the frequency and then you look at the responses at different frequencies. Today we're just going to use a single frequency, and I will show you in a minute why. Popular plot options, by the way, if you can imagine, like if you measure now the impedance, if you measure the phase shift, and if you are then calculating, for example, from that the imaginary and the real part of the impedance, you have like a lot of data that you can plot and need to plot. So there are different plot options that people prefer. In electrochemistry you find a lot the Nyquist plot, which is the negative imaginary impedance versus the real impedance, or the border plot, which is the logarithmic impedance versus the logarithmic frequency, and the phase shift versus the logarithmic frequency. So here you see the two plots, the border plot, which is actually two curves in one, as I said, with the phase shift and the logarithmic impedance, while the Nyquist plot is just one graph. Okay. This is a very interface sensitive technique, and little changes on the interface already induce drastic changes of the shape of, for example, the Nyquist plot. So you can see like water uptake in organic coatings. You can see like if the surface is corroding, but you can also see interaction between biomolecules. You can use equivalent circuit fitting to extract the contribution of single elements. That means we try to replace our electrochemical system with an electronic circuit that behaves in the same way. I will show you that in a minute as well. And then you can fit the data and this way extract the contribution of different single components. Right, this way you can, as I mentioned, detect corrosion before it's visible. You can check on coatings, as I said, for example, inorganic coatings and the water uptake, or organic coatings and the water uptake as well. You have label-free immunosensors. That means, as I said, interaction of biomolecules at the surface. So, for example, if you have a DNA measurement, you can skip the PCR to attach your electrochemical label, so your redox label, and instead using impedance spectroscopy and just see the interaction. Unfortunately, this technique is slightly complex, so if you want to give it to end users for direct usage, you often need like a special surface software that is completely processing this data for you immediately. Okay, today we want to measure conductivity to then correlate that with salinity, and we can do that by first representing by thinking about ourselves first. If you think about it as an equivalent circuit, it looks a bit like you see it on the left side. And I'm not going too much into detail, but what I want to say is at high frequencies, the solution resistance is the main contribution. The solution resistance is the one that's now in the right circle, that is this resistor. And if we have high frequencies, most of the currents will go through the capacitor, because a capacitor has, at high frequencies, a very low impedance, and so most of the current will go through this resistor R1 and through the capacitor C1 that basically has no contribution to the impedance. Okay, then we talked about conductivity a lot, but actually what you get is when you measure the resistance and you have the inverse, you get the conductance. For AC voltages, if you're like very strict, the inverse of, so 1 divided by Z would be the admittance, right? But today, as I said, we're going basically to extract only this resistance, so we can work with the resistance and don't have to work with the, we can work with the resistance, turn it into conductance, and don't have to go the way through the admittance. Okay, so the conductance that you measure depends on the cross-section and length of the solution where the current is passing through, just like it would be in a cable, right? You know the concept of resistance in a cable, and well, the same is true for conductance in a cable and in solutions. You can normalize your conductance to get the conductivity. For that, we have the cell constant. This is something you can calculate rather easily for the classic setup of a conductivity measurement. There you have two parallel plates, and you know the cross-section where your current is passing through because they have the same area of the plates, and you know the way or distance your current is traveling by the length between the two plates. And this way you can calculate a cell constant that basically normalizes your conductance to area and length. And then you get the conductivity, which is a solution property specific for this solution. Okay, but yeah, and then I said the salinity correlates with the conductivity. And we usually assume that sodium chloride is the dominant salt for most naturally appearing water sources. Okay, this was now the classic setup. You have two plates, and there are quite a number of probes that use that. And you see that here on the bottom right, the little picture, and you see the orange curve, how the conductivity behaves over, so how the signal from your probe behaves compared to the conductivity of the solution. Right? Take care, these are both logarithmic scales. The classic probes are a bit big and don't have always optimized cell constant. And Zimmer and Peacock is of course very good at designing electrodes. So they designed an electrode for conductivity measurements that has a very low cell constant by providing a lot of area for the current to travel through, and have low distance between the two electrodes where the current is traveling. Okay, and with that small cell constant you could actually see that you get a better correlation between, well, a better longer linear correlation between the signal and the resistance of the solution. So while the probe is like giving up in ranges of, well, that would be like then most like 50,000 ohms, so 50 kilo ohms, the Zimmer and Peacock electrode goes all the way to the 100 kilo ohms in a linear fashion on a logarithmic scale, which is really helpful if you want to make especially software that automates all of this. Right, the cell constant in these kind of situations with the more complex cells is usually empirically evaluated and not calculated, it's just easier. Okay. You can find on the Zimmer and Peacock website, by the way, a calculator to even calculate the osmolarity, which is, for example, a popular measurement for biologists if they talk about conductivity and salt concentration, etc. And this is really helpful, but there has a limitation. It assumes that the conductivity is only based on sodium chloride, which is true for many situations, and it will serve perfectly your purpose. So just visit the website of Zimmer and Peacock shown at the bottom here if you want to easily calculate from your measured conductivity your, well, the sodium chloride concentration and the osmolarity. As I said, assuming that all conductivity is contributed from the sodium chloride. If you actually want to measure the real, for example, chloride concentration or real sodium concentration, you would have to work with an ion selective electrode. Zimmer and Peacock, of course, has also a solution for that, for the ion selective electrodes. And just that would be a great point to all, you know, we're towards the end of the theory part, so to wake you guys a bit up. I have another poll. I wonder if you did already work with ion selective electrodes. And so we have a poll for that running also right now. Right? The most popular ion selective electrode is usually pH, but of course there are other ones, like for wounds it's interested to know the sodium or potassium content, but there are also other types of ion selective electrodes. If you want to tell us which ion selective electrode you worked, and it's not in the list, so it's the yes, I worked with another one, just put it in the chat what it is, and then we can later look at what you've done and then think maybe that's an interesting topic to talk about in a later webinar as well. Okay. Yes, so I am now looking at Adi to see if we have good progress at the poll, if we're like, should we already move on? Is that fine, the poll?
Yeah, just a few more, 40 more seconds for the poll to end. And we see a lot of questions coming in, so thank you all for responding.
Ooh, wow. So we already have a lot of questions. That's really good. And we didn't even have done the live demonstration. I think Solrun is really impatiently waiting to finally show us what you can do with the Zimmer and Peacock conductivity sensor and the Sensit Smart. Yes, so we'll just wait for the poll to finish.
Coming in, are people asking about new applications or just about impedance in general, Ardi?
Yeah, we have one question about the Sensit Smart and an existing sensor. And this is, I think, a good question to answer after the demo.
Cool. I must make a personal comment. I was pretty amazed when I realized the Sensit Smart could do impedance spectroscopy. I don't really believe it, because an impedance spectrometer should be about this big, you know, in terms of height and depth, and it should really weigh a lot. So I'm a little bit surprised that it does it, but it does it. So congratulations to PalmSens on pulling that one off.
Yeah, I mean, I have to say, like, spectroscopy, that was possible because we had a close cooperation with the company Analog Devices. It's a big company for making electronical components, and they have developed a special chip for that. And yeah, so we've used that to make this very small and powerful potentiostat. And I think this is really one of the main, well, advantages that it has. It has impedance spectroscopy at that size, and that will be, well, I think this is really outstanding. And I'm really excited to see all these people who finally can make the, yeah, label-free immunosensors. I think this is one of the most exciting applications for that. If you think you get enough DNA and you can do without a PCR an electrochemical-based DNA detection, for example, I think this is a really good thing. Also, I know people who test with impedance spectroscopy for Ebola or tuberculosis, and tuberculosis is still really widespread in a lot of countries. And so having a point-of-care test that you can just pull out of your pocket and do, I think these are exciting times for electrochemists.
All right, and before we continue the demonstration, I would like to tell everyone that if they have any questions, you can write them in the chat. You can write them in a public chat or a private chat, and then we will answer your questions after the demonstration. All right, and now it's time to go to Sauron for the demonstration.
Okay, so my name is Solren, and I will demonstrate to you how we are measuring using an impedance
Spectrometer, yes.
Yeah, for a sodium chloride solution with different concentrations. So this is the really neat small PalmSens Sensit Smart that we've been talking about, and it's connected with an adapter to one of the sensors from Zimmer and Peacock. So we will insert that into a smartphone.
It's probably worth saying it's a small little comment as Solron does that. But if you're looking for one of these holders for your smartphone, you can get a 3D printable file from us. We don't mind passing that on. And as we made you don't need this adapter particularly. You can run impedance spectroscopy in many modes, but there's 3 electrode mode, for example, and there's also 2 electrode mode. We happen to be measuring in 2 electrode modes today, and because we're full of engineers, we made a little adapter for us. We can also provide that as well if you're ever looking for it.
So I assume that you're now seeing my screen. So you'll go to method and you'll choose impedance
spectroscopy, yes.
Oh man, that word was really hard today. Sorry about that. And we'll make sure that the AC is 5 millivolts, and we'll do a fixed scan, and then we'll do time scan. We'll also use 100K frequency, hertz frequency, and then we'll go to the plot, and we'll start the plot. And now we're running it for 10 seconds.
Perfect.
So you see that it's running now, and it's running for the lowest concentration.
So we're in about 13 millimolar of sodium chloride, which is the least conductive solution that we have here today. As Solron said very elegantly, eloquently even, it's only 5 millivolts AC, so it's a very small sort of excitation. And the current response is indicative of the resistance, and the inverse of resistance is the conductance. So we're not doing the full, Nyquist plot where you scan frequency and you get, the real and imaginary. We're doing a simpler experiment, but this is a very powerful little instrument that you can actually do full impedance spectroscopy.
Yeah. So right now we measured the impedance, and we'll switch to the conductance. And as Lutz was saying earlier, you get the conductivity by multiplying the conductance by the cell potential.
Cell constant.
Cell constant.
That's fine.
And for simplification, we'll assume that the cell constant is approximately 0.5. It is approximately 0.5, but more like 0.4 something. But yeah, for simplification, we'll do 0.5. And here you can see where the blue line is. That's the conductance, and that's approximately 0.88 right now, which means that we have a conductivity of approximately, so that's 0.88, which is 880 microsiemens. So the conductance then is 440 microsiemens per centimeter. So we'll do the same for the next concentration, which is a bit higher. So this was a concentration of 2.67 millimolar. And we'll now do the same for approximately 11 millimolar of sodium chloride. So we'll redo the measurements and clear previous data. And now we're running it over. Again, you can see the impedance, as this is impedance spectroscopy. And yeah, 10 seconds, we'll again swap to conductance. And here the conductance is approximately 3.2 millisiemens, which is 3,200 microsiemens. And multiplying that by 0.5 for the cell constants, we get approximately 1,600 microsiemens per centimeter for the conductance. So you can see that the conductance is higher than that for 2.67 millimolar.
I just want to say, I mean, Solron her background is quantum chemistry. So if you're wondering why her mental maths is quite so good, this is because this is easy for her. So just as way of background, but yeah, good mental maths.
All right, and then we'll see if I'm able to nail the last calculation.
No pressure.
So here the concentration of the sodium chloride is 42 millimolar, and again we'll run the spectroscopy, the impedance spectroscopy, and we're running it for 10 seconds yet again. So it's quite fast, and you can deal with quite a lot of different parameters. We're using 5, the DC is 5 millivolts right now, but you can also go for 50 depending on what kind of solution you have.
Yeah, you could always optimize the excitation to get the highest, let's say, strength signal. I mean, as Solron runs this one, I mean, 50 millimolar is kind of interesting because I think blood, if you ever taste it, you can tell it's about 150 millimolar. sodium chloride. So the 50 millimolar now is kind of more representative of the kind of conductivity of blood. And there's kind of an interesting measure in the conductivity of blood. If you do that, you can start measuring something called hematocrit, which is the kind of ratio of liquid to red blood cells. So there's a sort of medical application for this as well.
Yeah, all right. So here I swap to the conductance measurements. And here we have, well, let's say 12 millisiemens, which then by multiplying it by 1,000, you'll get the microsiemens. And then multiplying it by 0.5, you get the conductivity, which this time will be approximately 60,000 millisiemens, or 6,000 millisiemens per centimeter, which is the conductance. And that was bigger than the other two solutions, which had a smaller concentration. So that's it for the salinity measurements. And so it's quite fast to do. And yeah.
Well, thanks very much. I mean, it's quite impressive, really, that such a small instrument, you know, with a sort of, you know, a low-cost screen-printed electrode, a small instrument, a smartphone, and you can actually make sort of 3 measurements like that. I don't know how long we've been going for, but, you know, 5 to 6 minutes, let's say. No, I'm really, really impressed with that. So in terms of Ardi and Lutz, you know, what are the kind of questions coming through? Do we need to take a poll? Let us know.
NP electrode would you recommend for sweat sensing? So it seems a bit like similar to salinity.
I think the question was which what was it? Which material or which geometry for sweat sensing? Just say the question one more time.
Yeah, which ZP electrode do you recommend?
Yeah, so at ZP, we've got a bunch of electrodes. We call them the gold 303s. So AU 303s. These will work pretty well. The big secret about measuring conductivity is you can buy an expensive probe for conductivity. It costs you a couple of €100. You can buy fairly low-cost screen-printed electrodes. You get the same performance. It's a sort of, but you know, the direct answer is it's gold 303s. We've been using it to measure things like conductivity of soil. It's just a side point, but the most knowledgeable person in our company on conductivity and impedance spectroscopy is behind the camera, so he's hiding there. But I just want to put a shout out to Mots. But the quick answer is the gold 303. If you Google that, you'll find an electrode that we can stand behind, and it works pretty well. Thanks, Ardi.
All right. Lutz, I also have a question for you. So there's a customer who already has a Sensit Smart, and he also has and this time a BVT gold SPE with silver chloride. Would it be possible to do a similar measurement like we just demoed?
I think it would be possible. We had customers who wanted to optimize towards the conductivity measurement, and they got the advice from that manufacturer, so BVT, to work with a different geometry that is a bit similar to what Zimmer and Peacock presented today. So with the Zimmer and Peacock electrode, you saw that it was like kind of a spiral, this design. And this is similar to what you find in other places. It's called an interdigitated electrode. That is usually like small fingers of electrodes that are like little interlocked without touching, of course. And the manufacturer themselves rather suggest to use these type of electrodes than the one that you suggested right now, which I guess is the AC1 design. And yeah, so they do not recommend it for it. I have, well, what I've seen from Zimmer and Peacock's research, because they have tested it with these classic electrode designs that they have as well, and it did work. I don't know in detail like what additionally errors you get and how long it is stable. I've not done extensive measurements on that. But usually BVT themselves, they suggest a different electrode. They suggest these interdigitated electrodes.
All right, thank you. And another one, Lutz. Does the AES signal that you measure on the Sensit Smart, does it need to be calibrated prior to do some analysis based on standard reading?
It already comes calibrated, so you don't need to do a calibration yourself. However, if you feel that you're not sure if it reaches the accuracy that you require, you can of course use the dummy cell that you get together with the Sensit Smart and test if it delivers the correct values, or you can even design your own circuits and do a test measurement. But it comes already calibrated and tested for different impedances. Maybe this is necessary, good question, if you use special electrodes and they already come with like a very high impedance. But of course, most of these types of measurements that you've seen here, and also I think for most analytical measurements, what you do is, because it's really difficult to understand all the influences and take all the influences into consideration, so you rather do a calibration curve with empirical values. So in case like just what you've seen with Solrun, she performs the impedance measurements. She would first take solutions where she knows the conductivity or the salinity, and then correlates the known values with the signal she gets, and then uses that calibration curve to make the real curve. However, our devices all come already calibrated to the customer.
Great, thank you, Lutz. And Martin, this is a question for you or for Solrun. It's about the sensor conductivity. Does it drift over time? Can you say something about that?
Funny enough, I think conductivity is actually a very, it's quite a robust type of sensor, because as long as you've got two electrodes that are fairly identical, so if they're drifting, they drift together. So in fact, it's actually, when I think about it as a measurement, nothing's forever, but in terms of failure modes, you often get the working electrodes, deteriorating, or the counter electrodes deteriorating. Well, in this one, as long as they're drifting together and they're made out of the same material, the impedance between them or the signal is due to the liquid between them, not due to the electrodes itself. So it's actually quite a robust technique. So if I was to sort of say, what's the easiest, let's say, biosensor to make, and get sort of robust values of? Is it a glucose sensor? Yeah, it's pretty good. pH, it's pretty good. Actually, I think conductivity is quite straightforward. So I think if you have a roadmap of things that you were going to do with your life, if you could find an application that was using conductivity, I think that would be a good place to start. Just FYI, if you're sort of unclear about some of these things, we do a webinar every Thursday at 8 AM London time, and we sort of answer technical questions there through our ZP forum, but just a quick plug on that.
All right, good idea. Thanks, Martin. Lutz, I also have a question for you. Are there any negative side effects that you know of if you run the Sensit Smart on its battery? Let it run for a while, or if there are any other side effects you can think of if you let it run on a battery?
Right, so the Sensit Smart itself doesn't have a battery. Of course, it depends on the battery of the device that you've connected it to. So as we saw today, when Solrun connected it to the phone, that was the moment the Sensit Smart was powered, indicated by the blue LED light. As far as I know, it is powered or it is not powered. So if there's not sufficient current provided, it will not work properly. As far as I know, we have not observed that if the battery of your smartphone goes low, the device will still be running but gives false results. I'm not aware that we have not observed this in our tests here, and we have not received feedback from customer that indicates this. So so I would say no, you don't have to worry about it. Except of course the problem is, I guess, like when the battery is getting old and what the telephone analyzes with the battery and says, oh, I still have 80%, but that's not true. It's 10 or 5%. Then of course there might be interferences, but for that we would have to try to get a very aged phone battery and try to figure that out. So we have not done this, but this is a very theoretical scenario now that I'm painting here. So
Exactly. So far, it doesn't affect the battery of your phone. All right. Thank you, Lutz. Martin, another one for you. Does Zimmer and Peacock specify any equivalent circuit elements? So the R1, R2, and C1, etc.
I think we might do. It's been a long time. But if you Google Zimmer and Peacock equivalent circuit, I'm pretty sure that actually we do have that kind of data on our website. So the quick answer is, I think we do have equivalent circuits on our website. Mots, who's behind the camera, thinks so as well, because he probably wrote them and I probably just cut and pasted them. But the quick answer is I think we do have equivalent circuits. Yeah, so you can probably find something on there as well, on our website.
Martin, these are then equivalent circuits for your electrodes that take the surface of the electrode into consideration. Is that what this is?
An equivalent circuit for like sort of doing conductivity measurements. I mean, you know, the equivalent circuit, as you know, Lutz, is going to be so simple, really. It's just a Randall circuit. You know, it's just, you know, a capacitor and a resistor in parallel and a resistor then in series with those. But the biggest impedance is the solution itself. So it's, you know, it's quite a simple, you know, there's nothing fancy about our equivalent circuits. Once you start putting a coating on that sensor, which we don't have, then you can, you know, start having more complicated equivalent circuits. And if you had a real redox molecule undergoing some electrochemistry, then you'd have a new type of equivalent circuit. But I mean, Solron said, I'm only putting 5 millivolts, let's say AC circuit on there. So if you're at low voltage with a tiny AC on top of it, you're having no electrochemistry. So the Warburg element is not there. You know, so it's really quite a simple equivalent circuit. Yeah.
Maybe as a remark on that, who's a bit interested in maybe also a few more complex corrosion-based equivalent circuits, you can also go on PalmSens.com to our knowledge base. We do have there also some information about equivalent circuits and equivalent circuit fitting, because like our Windows software PS Trace comes, for example, with an integrated equivalent circuit fitting module. So when you get our instruments, the software will have equivalent circuit fitting integrated.
All right, yeah, thank you, Lutz. Let's see, yeah, there is one more question. It's about AES, of course. Can a smaller distance between interdigitated electrodes, so for example 2 micrometers, and a larger number, as in for example surface acoustic wave devices, would it still work, or would it work even better than with the sensor that we demoed?
I think you tune the cell constant depending on the thing that you're trying to measure. So effectively, you're trying to measure resistance. So if you've got a high resistance, then you don't. You can have narrow. You know, 2 electrodes can be quite close together. The thing you're trying to measure is quite big, so you know you can get an accurate measurement. If your conductivity, let's say your conductivity was higher, therefore you need the electrodes a little bit further apart. So you can actually end up. So it's not necessarily that bringing electrodes together improves the signal. It really depends on the fundamental conductivity of your solution. And, you know, if you sort of, you know, look into cell constant versus sample resistance, then you can sort of optimize it. But there's a big thing in biosensors. Everyone wants to make smaller, more complicated electrodes. Sad truth is you don't need them. You know, you can have, you know, highly complicated interdigitated electrodes, or you can screen print down 2 rectangles next to each other and do it that way. It doesn't always have to be more complicated. At ZP, we're very different. When we're very interested in actually getting products to market. So when you're designing your electrodes, don't just think about the complexity of them, think about the manufacturability of them as well.
So keeping things simple is important, Martin. That is a perfect way to end this this question round as well. I would like to thank everyone for asking all these questions. If you have any more questions, you can feel free to send them to either PalmSens or Zimmer and Peacock, and we'll be happy to answer all your questions. Alright, so that's it. Thank you all for joining. Alright, Thank you.